So I want to talk today about more competitive solutions for increased efficiency on heavy-duty mobile machines, or let's say about ways how to achieve those more competitive solutions. And I want to start with the motivation of why we are talking about more efficiency at all. So what we're facing right now out there in the field are machines that mostly run still on diesel, which leads to emissions that are harmful for our climate. We see those negative effects, especially in recent months, more and more often, extreme weather catastrophes. And the only solution that we have right now, which is feasible on a large scale, is to electrify using batteries. So, wait, is it? It's working, yeah. So that way we can reduce the emissions. However, if we simply swap the prime mover here and don't do anything else, that means we're still left with the conventional hydraulic systems. There seems to be a delay. And those systems are based on valve control, which involves a lot of losses. Controlling a valve is basically the same as controlling a throttle in your car. So you produce a lot of heat, and in fact, efficiencies in the range of 20% only, meaning 80% of the input energy is lost into heat. Those are quite common numbers that you can see in literature. And the problem with that is that we might not be able to cover the demand for those machines then only with renewable energy sources, and we rely on fossil power plants in the end, which still leads to global warming. The batteries have to be quite big, which leads to high costs with the prices that we see at the moment, or the run times are rather short, in many cases too short. So that's a problem, but there's a solution again. We can swap those conventional systems with more efficient systems, therefore reduce the demand on the grid, reduce the battery size and costs, or with the same batteries extend the runtime, and we might also be able to electrify much bigger machines than we could before. So knowing that now, we need more efficient systems. It's actually surprising that if you look at literature, there are already quite many concepts for more efficient systems. Here just a few of the major groups of hydraulic more efficient concepts. So the question is, why have none of those concepts entered the market so far? That was basically also the starting question for my PhD research, and I tried to approach this topic by looking at the challenge like looking at the puzzle. So we have applications, this is here the green puzzle piece, and our task is to find concepts that fit into that gap. Basically we are in the workshop and trying to make a puzzle piece that fits the shape. But as Tyrone already mentioned, this industry is characterized by high variety of different machines. So the puzzle pieces that we need to fit might look very differently. And we need to find an efficient way to make our concepts not fit into one gap, but as many gaps as possible. That would be a very efficient way to do it. So my question was how to do that, and to get to the solution, you need to understand the problem. That's why I looked more closely at the interactions of the puzzle pieces here, meaning the characteristics and attributes that define how well my concept fits to a certain application. And the first question, I looked at the interaction between electrics and hydraulics. What happens if we start electrifying? So here are my key findings, which might not be new to most of you, but more details about this in my dissertation if you're interested. But basically, main advantages if you electrify is that you now have a very efficient way of distributing your power. Electric components are quite efficient. And also with electric motors, we have more control capabilities. We can control torque and speed of the motor much better than with a diesel engine. And also we can distribute more flexibly with electric cables, for example. However, we add costs usually when we electrify. So electric components are much more expensive than hydraulic components, and maybe sometimes it's also an alternative to consider adding a pump, which adds some more control degrees of freedom than adding an electric drive, because the costs would be not that much higher. Furthermore, electric components add weight and volume, sometimes at locations where you don't want to add weight or volume. If you have compact actuators that are located far remotely on an excavator arm, for example, that can be critical. And what is also often neglected is the auxiliary systems that you need for electric drives, cooling systems, for example, or all the components that you need to connect your high voltage components that can also easily add cost, especially if you have many of those electric drives on a machine. And last point, recuperation. There are also two sides for this. Of course, it's nice that we can recuperate. On the other hand, if we recuperate through the electric path, we have to go all the way back to the battery and back to the system, and there might be several components involved, so the recuperation paths can be quite long, and sometimes might be a better idea to try to recuperate earlier, more directly on a hydraulic or mechanical link between actuators. The next question then looked at the green puzzle piece here, so what are the characteristics of the application that make a difference? And the key findings here, I tried to look at them in two levels. First level on the actuators itself. So if we consider those parameters connected to the concepts, the size can have a very important impact. Some concepts, for example, struggle with very long actuators or large actuators. And the energy turnover can be very different. If we look at one cylinder to another, one might be actuated only a few times per hour or less, and another one might work constantly with very high loads. It makes a difference. And also recuperation potential, for example, can be very, very different between two different actuators on the same machine. And if we go one level higher, look at the machine and the mix of actuators on one machine, it can be very different. Some machines only have those high energy turnover actuators. Some have just auxiliary actuators because they otherwise drive all the time. Number of actuators can be very different. The scissor lift, only a few, and then some hydraulic attachment for a tractor with many different seeders, for example, can have a few dozen actuators on the same machine. Sequence of actuation is also important. Do I do everything in sequence or also in parallel? Can make a big difference for the efficiency of a system. And also ratio of driving between working can be very different. So we see wheel loaders, for example, sometimes in some applications driving all the time and not moving the arm a lot. But then excavators, they usually use the cylinders all the time and don't drive that much. So that also fits to the last case. The variety of use cases can also be very important. Also what we mentioned before with Theron's talks, if I have just one use case, it's easy to do a total cost of ownership prediction. In some cases it's not, and then it's harder to justify more investment costs, for example. And the last analysis question here was about the concepts that already exist. So what are findings there that can help for finding new concepts? Starting with the conventional systems, I mentioned valves can produce a lot of losses, but this strongly depends on the operation conditions. So if you just have one actuator, for example, even with valves, you can achieve a quite efficient system, but if you have multiple and have to operate in parallel, then you have those negative effects. And another finding is that those many new concepts which I showed before, they're often based on non-standard components, which look very cool in the operation conditions, but if they're not existent yet, it's very costly to develop them and manufacture them efficiently. So that's also concerning the next point. Many of those components that are required for new systems are quite costly and at high costs per actuator. And then if you remember before, we have some actuators that don't have a large energy turnover, so it doesn't make sense to invest a lot there. So there can be issues. Then what I mentioned before, also with the recuperation, there are some concepts which are especially efficient because they have this direct recuperation, so that's something you should try to involve as much as possible. And another aspect that's usually the key of having higher efficiency is individualization, supplying each actuator by itself instead of centralized supplies where you have to somehow get the pressure levels to the same limit, to the same level, which you usually do by throttling. So I used those answers to the first three research questions to define those aspects of importance, I called them, which focus efficiency as well as costs and feasibility, and use them to find answers to my challenge, the solutions here. And the idea was not to invent something totally new or something disruptive, but to use those elements of existing concepts that were promising. And the key is to use them in a modular way and synthesize them in a modular way so that you can change your shape of the puzzle piece just by using your existing pieces and not creating something totally new. And that way finding different puzzle pieces that fit our different applications. And those solutions, I had two different concepts that I looked into in more detail. First one here, and you can also see the modularity now. There are two options. So the green one, more innovative option for higher efficiency, also some higher costs, but that's why we have the second option, which is basically conventional valve control, not super efficient, but you can save on costs, basically for those actuators where the energy turnover is low. And the concept here in the green part is to apply back pressure by using this, is the pointer working? By using this assembly of hydraulic motor and electric generator to apply back pressure instead of creating pressure drops at the valves. So instead of throttling, we can recuperate energy here. However, the downside is that the recuperation path is quite long, meaning we have losses in the transmission when we recuperate. And another issue is that the actuators in the system, the cylinders, differential cylinders, they act as pressure amplifiers in certain conditions. So that's why we have this throttling valve in the supply line to limit the pressure at those conditions, which means at some operation points we have throttling again. So a few downsides, which is why I looked at this system only through simulation and focused rather on the next system, next concept. Also here, the modularity, well, through having a highly efficient solution, now the concept is to use a separate pump or additional pump for those actuators, which supplies only the energy that I need for each actuator, so I can avoid throttling, and also I can use this pump to recuperate. And then I still have the low-cost option, the conventional valve control. So I already mentioned I can recuperate, and I do so through the mechanical shaft ideally, and only if there's no consumer I store in the battery. And the challenge here is only the biggest challenge I found, but I could also solve, is handling the differential flows of the cylinders here in the closed circuit. That's why we need this accumulator assembly here. But yeah, all in all, this was quite a successful concept, which I first tried to show through simulation, showing the energy efficiency performance of those systems. So I had this setup where I looked at machines, basically here shown for 2 cylinders, and for each I can choose between conventional, so the low-cost solution, or one of the 2 improved solutions according to concept A or B. And then this was modeled in AMISM, the electrohydraulics, in order to have the same benchmark for each setup that I created that way. I always used the same load forces from measured reference cycles with real machines. And my controller was following the trajectories that were also measured in the reference cycle. So that way, all the different setups that I combined here, they fulfilled the same cycle, the same work energy, so I could compare them on a similar basis. And I did this for 3 different machines. Might look a little confusing on the first look. Have a look at the paper if you need more time. But basically, we have those setups A's according to concept 2, and then we have different configurations. For example, here only the boom actuator is improved. Here it's boom and telescope. And then the same is done with concept B. And for the excavator, we also have 3 actuators, so there are some more combinations. And yeah, the largest savings could be achieved, of course, if we apply more of those more efficient actuators. And then it's 37 in the cycle mix at 3 different cycles. For the telehandler, very similar, 36 for the wheel loader. So we could see that those 2 loader machines, they are very similar in the way they are operated, also achieve similarly high savings. And then the excavator, which is a little different from those machines, could also achieve much higher savings. Basically, the potential is higher because we have more parallel operation of those actuators and can reduce the losses that arise that way. However, what I marked here is other setups, not necessarily the highest, the ones with the highest savings, but those where we add only a few additional components, so just 1 actuator is improved, but still we achieve relatively high savings. So I marked those because those are probably the ones where we have the most efficiency out of added costs. So it's about the economic factors, and that's also why I conducted a total cost of ownership analysis for concept B and for the telehandler. So I considered the difference in investment costs between the setups, where my benchmark is all the actuators being valve controlled, so conventional. And then I also had two different scenarios where the costs for batteries, energy costs and amount of work varied a little bit. So this is more in favor for the more efficient system, because here we see, because the battery costs are quite high, it was 400 euros per kilowatt hour in this scenario. Only because we are more efficient, we can save that much on the battery cost, that the additional costs for hydraulic components can be compensated, and we even start off with lower costs, and over time, because the energy costs are lower, it gets better and better. And even if the costs are rather high and we can't compensate the additional costs for hydraulic components with the battery cost, with this setup 2, where only the boom is improved, we achieve turn-back time of less than 3 years, because the savings in energy costs are so significant. And as a reference, we see the working hours on the top here, so 10,000 up to 20,000, that's common for those machines. So the payback time is reached, early enough, I would say. So the last thing that remained to be proven, I showed before, it's about efficiency, cost, and feasibility. It's the feasibility, that's why I conducted experiments as well with this most promising setup and on the telehandler. For time reasons, we decided not to have the integration effort of putting the system into the machine. That's a lot of mechanical redesign of the machine. Instead, I built up this system on a stationary rack, placed the telehandler next to it, and had those hydraulic lines running there, and performed stationary cycles, adding some metal plates to apply loads to the telehandler as well. So that way we can prove the feasibility, because also experienced operators felt that it was quite smooth to handle the machine. Some of you could also see it during one of our more workshops. There were some new learnings about what I mentioned before, the handling of the differential flow, and also the simulation results about efficiency could be confirmed, because the measured energy savings were in the same range for similar cycles than for simulation. So that way I want to conclude. I tried to conclude it with those 4 points here. So motivation for this whole research is that efficiency is the key for electrifying and contributing towards stopping climate change. But if we do so, we cannot simply focus on efficiency and try to find the most efficient concept. Sometimes it's better to find efficient but not most efficient concepts that also keeps cost and feasibility in mind. And I could show, I think, that modularity is a very promising concept in this regard. And I could also show that there are solutions already available by using standard components off the shelf. So people just have to believe in the total cost of ownership calculation, I would say, and convince their end customers, and then there's already a good solution available, I would say. With those words, I would like to finish. Thank you for your attention, and feel free to ask any questions. Of course.
What is more important, efficiency or productivity?
Of course, productivity should be part of the total cost of ownership, I would say, in the end. So my assumptions here were that all systems were equally productive, while actually by adding more pumps, you don't run that often to the problem of flow saturation. So you could operate faster as long as the operator can handle it. But I would say that's part of the total cost of ownership calculation. And if you're less efficient but still cheaper because you save that much on other costs, it might be accepted. But otherwise, I would say your productivity should be similar to the previous systems or even better. But we see that actually with a more efficient system that they tend to be more productive as well. So I don't see a showstopper here.
Okay. If I understood it correctly, the suggestion to not go for two disruptive solutions was because, like you said, many new concepts are based on rather expensive components. And so first of all, is this, or how much of a projection is there? So that you say, it's costly now, but in 5 years, and especially if we implement these solutions, we could be first, and then also the costs could drop. So that's one part of the question. And then second, another dimension is that you might be a company like Liebherr, if I remember correctly, where you say, okay, we can produce this maybe ourselves. Or whether you are completely dependent on by purchasing.
By itself, I would agree that it can be disruptive if it's more expensive right now. We should invest, and it's even the cost won't be a problem in the future anymore. But so far, we see that the more disruptive systems, it's not just about scaling, and we need to have those manufactured in scale. It's just that, for example, hydraulic transformer, that's an element that you would need for each actuator, but it has the size of a pump and also the cost of a pump because there's so many rotating parts in it. So some of those components which are more costly are simply more costly because they are more complex, and this will remain that way even after a long time. Was there a second part which I didn't answer in it now? Yep. So that's an important fact because you need to have the engineering capability to apply not only to develop those components and make them cheaper, but also the effort to integrate them into your systems. For example, you might want to use electromechanical actuators because they're more efficient and electric, but then they have longer installation lengths, so you need to adjust your mechanical kinematic chains on the machines. That requires, again, not only engineering in the powertrain, but also in the mechanical department. And many of the smaller OEMs which we have in this industry, they simply don't have the capacity to do this. So they want to do the low-hanging fruits, which is using off-the-shelf components and doing it as simply as possible, but having the highest impact that you can have with that step.